Okay, welcome everyone. Thanks to all of you for joining. Welcome to the fourth edition of the Pawsey Supercomputing Series event. My name is Komati Padmanabhan. I lead the data science and AI platform at Monash University. I also lead the National Machine Learning Community of Practice in collaboration with the Australian Research Data Commons. As Karina said, I'll be moderating the panel today. Before we begin, I acknowledge the traditional custodians of the country throughout Australia and their connections to land, sea, and community. We pay our respect to their elders past, present, and extend that respect to all Aboriginal and Torres Strait Islander people today. So HPC in Australia has been growing, and we all know the technology has been shifting drastically. Pawsey is currently commissioning its new supercomputer as part of the most significant upgrade to Pawsey's computing infrastructure since the center opened in 2009. The new system will be named Cetonix, the quokka scientific name, the most friendliest animal. The system will deliver up to 50 petaflops or 30 times more compute power than its predecessor system, Magnus and Galaxy. This will hopefully help power the future high-impact Australian research projects. Cetonix is going to be delivered in 2 stages, with the first stage due later this year, immediately increasing the computing power of the center by 45%. And I'm sure we'll hear about that from Pawsey colleagues here. Phase 2 will be available by the middle of 2022. So Gaudi and Cetonix deliver more compute power than their predecessors and also make new technologies available to the researchers. So giving some introduction about the supercomputing event series itself, I think the series seeks to inform and inspire the growing community around supercomputing, the range of sciences, as well as the industry it facilitates. Pawsey has already hosted computational fluid dynamics, bioinformatics, and astronomy sessions in the past, and you can watch the recordings on Pawsey's YouTube channel. So one of the primary purpose of this seminar series is to address 2 fundamental questions. 1, what does it mean to scale? 2, what does it mean today? What does it take to scale in the context of HPC? And I think we'll be exploring these questions throughout the panel discussion today. As part of this series, we are interested in learning about the challenges and new possibilities that would be enabled by the next generations of the computers in relation to specific domains. Today's focus is specifically on artificial intelligence and machine learning and the impact our next generation system will have on it. So this virtual event brings together leading international and national researchers in this field to discuss current challenges and the capacity for discovery and acceleration that modern computers like Cetonix will enable. So we want to explore the research possibilities that we can expect to see in the future as scientists leverage major leaps in technology and look forward for exascale computing in order to tackle some of Australia's and even the world's most significant challenges. As Karina mentioned, at the end of the panel discussion, we'll be taking questions from the floor. So on the panel today, we have Dr. Alessandro Rigazzi, Dr. Ivy Wong, and Mathieu Cocho. Dr. Alessandro is an AI and machine learning engineer at HP Enterprise and a member of Cray Labs. He's currently a developer of Smartsim and SmartRedis, 2 open source libraries developed and maintained by Cray Labs at HPE. Smartsim and SmartRedis enables fast integration of AI and traditional HPC simulations. Welcome, Alessandro. Dr. Ivy Wong is a radio astronomer and CSIRO Science Leader working on massive data challenges in the era of square kilometer array. Using large all-sky radio surveys, Ivy studies how galaxies form stars, how central supermassive black holes grow, AGN, and how AGN affect the star formation history and the evolution of galaxy. Ivy, I'm sure you have a very interesting job. Ivy obtained her PhD astrophysics in 2008 from University of Melbourne and has previously worked at Yale University, CSIRO, and International Center for Radio Astronomy Research at the University of Western Australia. We also have Mathieu Cocho, who works as data analyst at the Carnegie Clean Energy with a Master of Engineering from École Centrale de Nantes and nearly 10 years experience in the marine renewable sector. He has gained extensive knowledge in simulation, design, and operation of wave energy converters. At Carnegie, Mathieu is the technical lead on the design and testing of controller of the CSIRO technology, which I'm sure he's going to be speaking about today, He's also involved in the development of various elements of AI, which include supervised learning for wave prediction and reinforcement learning. Also, we are joined by Pawsey's Head of Scientific Services, Dr. Mathieu Cocho, and computer scientist Christian D. Petrantino. Sorry, Christian, if I got it wrong still. And I think, I'm not sure Pawsey's CTO, Ugo, is going to join us. We hope that he's going to join towards the end of the session today, as he's held up in some other meeting. So to speak about Dr. Mathieu Cocho, Mathieu joined Pawsey Supercomputing Center in 2017. He holds a PhD in computational science. He's a mathematician and computational scientist, and has expertise in optimizing and developing applications on massively parallel and accelerated HPC systems. Since 2004, he has been involved in many HPC projects, including porting weather prediction codes to Cray X1E vector architecture, accelerating astrophysical computational kernels on IBM cell processors, and so on. Mathieu is currently the head of scientific services at Pawsey and responsible for delivering supercomputing. And I'm sure we're going to hear from you, Mathieu, more about Cetonics today. And Christian is the computer scientist working as supercomputing application specialist at Pawsey to apply his parallel algorithms knowledge and GPU programming skills to solve HPC challenges. Prior to Pawsey, he had worked in...
Christian, would you mind continuing your introduction?
Oh, sorry. I thought it was me actually who dropped out at first. Yeah, I'm working as a supercomputing application specialist now at Pawsey. I'm very interested in GPU programming and parallel programming. Before that, I was working in Italy in the National Research Center and doing the same kind of work I've been doing here, but at a much smaller scale. Now, with Cetonics, we have the possibility to work on such large-scale problems, and one of these is essentially machine learning. As I will say later, Cetonics will enable us to run machine learning workloads at scale, and we would like to develop the technology and the expertise to support this kind of workflow.
Thanks, Christian. I think I've dropped out and I don't know where I dropped out, but thanks for covering in between. I'm not really sure where I dropped out. Probably I might repeat something which I spoke about.
I guess you were introducing me and I did it myself. That's
okay, perfect. Thank you.
I think we can now go into the context and the first questions.
Okay, thank you. Thanks, Karina. So I think before we go into questions, some introduction towards what are we gearing towards, right? So approximately 2 months ago, during the 2021-22 budget announcement, the government revealed its $1.2 billion digital strategy. The strategy will target investing in emerging technologies, building digital skills, and improving cybersecurity. Also, an additional of $124.2 million will go towards developing Australia's AI capability over the next 4 to 6 years. The policy provides access to expertise and infrastructure in supercomputing, cloud services, data-intensive analysis, storage, and visualization provided to over 1,600 researchers across Australia. Researchers can currently access GPU capabilities for AI computational work, machine learning workflows, and data analytics at Pawsey via Topaz, the commodity Linux cluster with GPUs and InfiniBand infrastructure, and the Nimbus cloud as well. Cetonics, when fully available, will bring more than 750 next-generation AMD GPUs. This will definitely present new opportunities to researchers supporting AI and ML. So our first question goes to Mathieu. So Mathieu, you're part of the team shaping the future of HPC in Australia, and Cetonics is an example of it. So can you tell us why is AI important to researchers in Australia, and why are AI accelerators considered as part of the new technology that would be deployed in Pawsey?
Sure, thank you very much. Yeah, firstly, as a national supercomputing facility, we need to identify and support needs of Australian researchers, and we see a growing interest in using accelerators for both AI, machine learning, but also classical HPC or scientific simulations, let's say. And also as a side note, this is no different from other supercomputing centers. Interestingly, there are actually scientific methods developed to define how heterogeneous your supercomputing should be based on the currently supported workloads and projections on future demands, for instance, related to AI and machine learning. Such a scientific method was, an analysis was actually used and done by Pawsey in the case of photonics. Secondly, one of the important reasons for which we procured the AI accelerators, or namely GPUs that will be used in our system, is because they can accelerate and support both scientific simulations and AI machine learning workloads. And additionally, they are extremely energy efficient in doing so. So by porting your classical scientific simulation to accelerator, or in the context of today's seminar, by augmenting your algorithm in the simulation with machine learning, you not only reduce time to solution, but also you reduce the carbon footprint of your job, workflow, project, and the whole scientific domain. Some of you might have heard about the PACER program that Pawsey is running, and which was kicked off just recently, looking at scaling up scientific simulations and data processing workflows in various domains. In PACER, we see huge interest in using machine learning or augmenting scientific simulations with machine learning in a number of ways. One of the ways is to integrate it with the scientific simulation loops, for instance, by advancing in time, by using a statistical inference step instead of solving an actual equation, for instance. The other example is parameter optimization for instance, for multiphysics and ensemble simulations. And in general, any parameter optimization problem where values assigned to a set of parameters affect the accuracy of the simulation. Other areas might include feature extraction, which aims to reduce the number of features in a data set. And that's actually quite an interesting area as well. And this is not only to quickly extract information from large data sets, but also one example is object recognition radio astronomy data, where very noisy data sets have to be analyzed to extract the location. I guess we'll probably hear about that later today. In other words, machine learning techniques, looking at the whole research areas that we are covering, are not only used to optimize or reduce time to solution, but also to actually enable simulations at an entirely new scale. So for instance, you need to be able to analyze an extremely large data sets that are created during your large scale simulation that runs. So you basically, by increasing the scale of your scientific simulation, which is needed to improve the accuracy of your simulations, you are generating more and more data. You need to have appropriate techniques to analyze that data. So machine learning might be used in that context as like a post-processing tool to actually extract the important information. On top of that, we see AI being used in more traditional approaches, traditional AI approaches, for instance, for analysis of image-based data sets in agriculture, space data, marine and biosciences. A few other examples which are important actually for Pawsey in the case of few research projects that we are currently working with is our applications to medicine and health data in the context of automation and constant monitoring of patient conditions, applications to visualization to enhance the visibility of features of interest in complex data sets, for instance, in relation to very complex structures like turbulence represented in some of the CFD simulations. And last but not least, data compression algorithm that can be used to reduce the size of the data sets that researchers are working with. So I guess that's it from me.
Thanks, Mathieu. I think one interesting thing is how, while we make all this decision, how the environment and sustainability is looked at as a key factor in decision making. That's very good to know. Thank you. So Alessandro, probably the next question is more towards you. So AI and ML are currently commonly used as tool to advance scientific discovery across various domains. However, not all scientists are performing some fundamental AI and ML research, right? So, but Alessandro is an AI researcher using a supercomputer to perform his work. Alessandro, can you please tell us about your research?
Yeah, sure. Thank you. So my team is the Cray Labs at Hewlett-Packard Enterprise, and we develop and maintain, as it was already said, this open source library, which is called Smartsim. So Smartsim tries to bridge the gap between traditional simulations and AI. Basically, for years, we've been promised that there will be a convergence of AI and HPC simulations, but for scientists, there are still barriers. And one of these barriers is that basically traditional simulations and AI speak a different language. So traditional simulations are written in traditional scientific languages like C, C++, and Fortran, which are historically very powerful languages. But at the same time, AI and machine learning usually speak Python, basically. So you have PyTorch, TensorFlow, Onyx, all these toolkits which are written in Python, and merging the two worlds, let's say, is usually difficult because either you create an ad hoc solution for each simulation, but this is really expensive for scientists because the time is a hard constraint for scientists, or you try to avoid merging them and you rewrite parts of your code and parts of the AI library. So really our library tries to make closer these two worlds, and so that you can really enjoy AI and ML in your simulation without modifying your simulation so that you have to spend days and rewriting things. We believe this approach is extremely powerful, especially on supercomputers, where you will be able to run at the same time simulations as you've already run simulations in the past, and AI side by side, and then let them communicate with Smartsim.
Thanks, Alessandro. You've also been working with a team from the National Center for Atmospheric Research in US to develop the first climate scale numerical ocean simulation using Smartsim. So can you please talk us through what it is about and its impact?
Yeah, sure, thanks. So with the National Center for Atmospheric Research, which is NCAR in the US, we put together a demonstration of what Smartsim can do for scientific, for example, climatology, but for the scientific world. So they had a very powerful simulation, which they use in production, and is using a very, very old code, let's say, or well-established code, which is called MOM6, Modular Ocean Model 6, I think. And this code is written in Fortran. So trying to add AI to that simulation was very painful. We inserted just Smartsim, and we could use AI together with the classical simulation. And why did we have to do this? Well, there are things that at some resolutions, so when you do a simulation with a certain scale, certain quantities like the eddy kinetic energy are very difficult to predict with mathematical models. There are mathematical models which work on high resolution models, but usually in production you use low resolution models. And so what we did was to train a neural network on high resolution models and then use it in the low resolution simulation through Smartsim. So basically within the Fortran code, we inserted just some calls to Smartsim, and the simulation was sending the data to other nodes where we had GPUs, which were processing the data with neural networks. And then the results of this processing was sent back to the simulation for the next time step. So in that way, we didn't replace really something existing in the simulation or something working in the simulation with AI. We just added AI to enhance the simulation and to get where with pure mathematical models was impossible. And the results are very, very exciting. The community reacted very positively because it was the first time that certain structures in the turbulent flow of the oceans could be reconstructed with this kind of simulation. And so for Smartsim, it was a great breakthrough, and I invite everybody to look at this study we have with NCAR, Smartsim, because it's a really, really good scientific work.
Thanks, Alessandro. I mean, if possible, if you can post a link to the work, I think that would be helpful for all the participants here. So moving forward, Matthew, probably the next question is towards you. So from parameterization of oceanic turbulences to wave prediction, the process of testing and validating the CSIRO technology, Carnegie Clean Energy has developed a wave predictor using Pawsey's GPU system. So Matthew, can you please tell us about what is this wave predictor? Why is it important to Carnegie's digital development pathway? And what is its potential for other industries?
Sure. Thank you for the question. Over the last 18 months, the team here has been working hard to drive down the levelized cost of energy of CSIRO, or LCOE, which is essentially how many dollars it costs to produce 1 kilowatt hour of energy. One of the areas we're exploring to do that is the area of advanced control, because it has the potential to increase how much power we capture from the ocean at limited cost. Now, if you look at the literature over the last few years about advanced control of wave energy converters, you realize that most, if not all, advanced control strategies rely on knowledge of the waves some tens of seconds into the future. And so that's why we've been working on the development of our wave predictor. When we looked at this problem, we wanted the wave predictor to be both fast in order to be able to work within a real-time environment of a controller, but also accurate in order to be able to predict waves in the complex environment that is the nearshore areas where we deploy CSIRO. And so machine learning was an obvious candidate for the application. So what we do is we essentially model wave prediction using deep learning neural nets, and based on wave sense data measured by wave sensors located upwave from our system, we can predict waves up to 30 seconds into the future. We've used both Magnus to generate synthetic data to train for training of the wave predictor, and also Topaz, the GPU cluster, to actually perform the training. In terms of applications to other industries, I think it has direct applications into any offshore industries that has operations that are wave dependent and limited. For example, transferring crew from a ship to a structure, or loading ships cargo from one ship to another. Both these applications would benefit from early warning of large waves, and so these obvious candidates for this technology.
Thanks, Matthew. Also, Carnegie also partnered with HPE to develop reinforcement learning-based controller for CSIRO. So what is that about, and where are you up to with that?
Sure. So Carnegie's looking at different control strategies for CSIRO, one of which makes use of the wave predictor that I just described. And this one is called Model Predictive Control, and is based on an internal model of the CSIRO system, which runs onto the controller. Now, this is quite a computationally intensive control strategy, just because it's optimization based and needs to run the model at multiple times at every time step. So to work around this, I guess, downside of this controller, we have the idea to look into reinforcement learning control strategies, where the idea is, just like we've seen robots teach themselves how to walk, the idea would be that CSIRO could teach itself how to operate optimally in the waves by looking at and interacting with its environment. To do that, we've teamed up with HPE Labs, who have bleeding edge skills in the area of reinforcement learning. And we've had some success, though it's still work in progress. We've seen improvements of upwards of 30% in comparison with our baseline controller.
Thanks, Mathieu. It all sounds very exciting. Ivy, probably now we're focusing more towards you. So Ivy, as I mentioned in the introduction, works with astronomical data with the Australian Square Kilometre Array Pathfinder ASCAP telescope. We have all heard of the desire to reveal the secrets of our universe, but Ivy, how is AI and ML being used by astronomers in their research for the unknown?
Yes, so as an astronomer, I'm most interested in surveying the sky, the universe, further, deeper, wider, faster, at higher resolution. So I sound like I want it all, and for once, we're getting the data. So there are projects within ASCAP, the Australian SK Pathfinder, that could be receiving like 200 terabytes a day. And at such a data rate, this is just the raw data. So we're exploring the use of AI without machine learning to automate the processing, the analysis, and the discovery of things. So you can actually think of our application as trying to build a planned serendipity type machine for various projects.
Well, Ivy, can you also speak to us more about how applying AI or ML is used to accelerate the ASCAP scientific outcomes itself?
So I cannot speak for all the different project teams, but I personally have explored the use of simple AI and simple machine learning methods, such as very traditional machine learning methods such as k-means or just different principal component analysis, all the way to single layer networks versus the application of deeper networks through multi-layer ResNets and GANs, and all in the hope of looking through our data set, whether it's just data tables or images, to look for the separation between what's signal and what's noise. And so at the moment, given the size of the data sets, just dealing with the size alone is a pretty interesting task, much less creating ground truth labeled data sets. So, exciting times.
Yeah, I mean, you touched on the size of data, right? The size of data is challenge to any scientific field, but it's an understatement when it comes to astronomers. We know the amount of data that's being collected, right? And the challenge itself is, I think, which is all everyone is hearing about. How do we make decisions on what data needs to be, specifically what raw data can be retained or what can be discarded? So in that decision, do you think, is it possible that AI can help you make that decision?
Oh, definitely, because at this point in time, it's much cheaper to reobserve if there was an automated way for us to say, actually, the current data set that just came in is mostly rubbish. Let's delete it and start again, simply because processing bad data takes more time than actually reobserving and then processing it well. So the processing time at the moment takes much longer than the time it takes to observe a certain object. So in this particular manner, if we could automate this process, we could significantly improve the workflow.
Sounds like one interesting project coming up. Yeah.
Oh,
So multiple, yeah, definitely. So now that we touched about challenges, Alessandro, I'm going to probably move towards you to ask. It seems that the Smartsim, you're moving towards overcoming some of the challenges in AI, such as the diversity of programming languages, dependence on I/O, and large variance in computer resourcing requirements. So what other challenges are AI and ML currently facing? Are supercomputers part of the answer or part of the challenge or problem?
Yeah, I am pretty sure it will be part of the solution. Supercomputers are incredible machines, and I don't say this just because it's my business, but really, I'm a supercomputer fanatic, I would say. So for sure, AI and ML are wonderful tools, but many times they are used in isolation, or they're used in a less performant way than what could be done. Especially when we, for example, train them offline on small data sets, which we stored from a simulation we ran before, and maybe we had to store everything on the disk, and so we have a read from disk delay when we want to train, for example, a neural network. And Smartsim and future supercomputers will make it also faster to train on the data you are producing with simulation at exactly the same time, right? And supercomputers, especially Photonics, which will be a great system, will benefit also from the Smartsim approach of separating the AI and the simulation workloads, so that you will be able to use the accelerators for AI, for example, and the non-accelerated partition, if you want, for other parts of your computation which don't require it. And this will be possible thanks to the next generation of supercomputers at Pawsey. The interconnect, which will be new HP interconnect, will be super fast for this type of work. So it will also be a great improvement. And AI and ML will finally be used by scientists who are not maybe ML and AI domain experts in their basically in their research, right? In what they know better. And that's the great thing that Smartsim and the next generation of supercomputer will offer to scientists, I think.
Thanks, Alessandro. And I think we'll hear more about photonics from Christian soon, right? So while we're still on challenges, Mathieu, Carnegie is using GPU accelerators at Pawsey, but also accessing GPU capabilities through Microsoft AI for Earth grants. What are the challenges wave energy research is facing that can be overcome with neural networks, and are accelerators part of the answer?
Sure, thanks for the question again. I think one of the large challenges we're facing in wave energy is the constant trade-off we're having to make between the accuracy of our simulation tool and how long it takes to run a given simulation. And it's very related to what Alessandro was discussing before. To give you an order of idea, in order to run a 10-minute long simulation on Magnus of the CSIRO system, the runtime is in the order of 24 hours, and we get very high accuracy results. On the other hand, running the same 10-minute simulation using simpler tools takes seconds, but we get a much lower accuracy. And there is nothing to bridge the gap, I guess, between those tools. I think where AI and ML could play a great role there is, AI-enabled CFD simulators would be able to fill that gap, to bridge that gap, and give us access to very accurate results in a fraction of the time it would take a traditional simulator to solve. And that has repercussions in a lot of areas of our, work. The first one being control, with, for example, the wave predictor that I was talking about before. The other one is just simply design. Designing CSIRO is a very complex task with a lot of parameters you have to vary in order to land on the optimum design. The design space is huge, and the number of simulations you need to run in order to find the optimum design is also huge. At the moment, what we're having to do is to use low fidelity simulation tools to sweep the design space and run only a few select cases on Magnus using high fidelity tools. Using AI-enabled, this process is what we're doing at the moment, but it only gives us a partial answer. Using AI-enabled CFD tools would allow us to sweep the design space with high accuracy and give us a much better answer. Now, into the second part of the question, whether accelerators are part of the answer, I think they definitely have a crucial role to play in helping us solve this problem. For example, when I moved the training of my supervised learning models onto Topaz, I noted a speed up in the one order of magnitude, and so have HPE when they started training their reinforcement learning models on their GPU clusters. But these accelerators, I guess, are not only relevant for ML applications, but also for more traditional simulators like OpenFOAM, where we're seeing more and more libraries coming out to enable tools such as OpenFOAM to use GPUs with, I guess, speed ups in the order of magnitude as well.
Absolutely. Thank you. Thanks, Matthew. Let's hear from Kristen on some updates about what's happening there. So Kristen, Pawsey is currently about to hit some important milestones as part of the 70 million capital refresh project. Can you tell us what's happening and why are these puzzles important for researchers working with AI and ML?
Yes, Komati. So the past months have been very exciting and also intense for the Pawsey team, which I'm part of. We have been working on several fronts to prepare for the arrival of Setonics, the next supercomputing system of Pawsey, in order to have it ready for researchers for the next allocation round, so the 2022 allocation round. We've been training ourselves on this new technology. There are many new things, and we also have been preparing in turn the training for our users and researchers. We've been also benchmarking applications, libraries, and frameworks, and but also working on documentation as well, documenting the new features and the new system. And it's only a few of the activities we've been working and focusing on. We've been also, of course, working on the system configuration and management because new opportunities arise when the new technology are available. We've based this work on our experience and expertise from past systems, but also a crucial help arrived from collaborating with peers infrastructures all over the world. Then we've been working on the PESAR program. PESAR is an acronym for the Pawsey Center for Extreme Scale Readiness. And it's a program that whose objective is to prepare Australian researchers to take advantage of the next generation supercomputing infrastructure. In particular, in the last year, we have had access to an AMD provided test cluster, which provided us with access to several new technologies, AMD CPUs and GPUs, where we could experiment with this hardware, but also the software framework that comes with it. The thing is that the system wasn't configured to be a supercomputing environment, an environment that, for example, HP provides. In fact, in the next it's imminent the arrival here at Pawsey of the test and development system, a system provided by HP, which represents what we can say a small portion of what Setonics will be, and it's available to Pawsey team to test, configure, and fine-tune the environment that will be ultimately available on Setonics. And so with the arrival of this test system, we are and then the phase one will be available at the end of the year to Pawsey team to prepare it for the next allocation round. With the test and development system in particular, we are looking to expand also our expertise on machine learning workloads. Machine learning is an area which, at least in Australia, wasn't until recently actively supported by the supercomputing infrastructure and the supercomputing expertise represented by the various specialists working in a supercomputing center. And we are looking to change that. We are actively working. We look towards working on defining fine-tuned environments and best practices to support machine learning workloads. This is because Setonics will provide us the tools to support such kind of workload.
Thanks, Christian. I'm sure, I mean, that's all exciting, and I'm sure many of your users will be excited to have their hands on Setonics soon. But what are the main limiting factors to successfully execute AI ML workflows in your in Pawsey's current systems? And how can Setonics help improve these things?
Yes, so our current system, our current supercomputer is Magnus. We have also a few smaller systems, a few clusters named Topaz, Zeus. And the main problem with the supercomputer we have, I think it's a supercomputer made of 1,500 CPU-only nodes. Each node has 64 gigabytes of RAM available and 24 cores. While it has served the scientific community well in the last years, Magnus is now obsolete, and in particular cannot support, with that kind of characteristics, cannot support the machine learning workloads, especially the today's ones, which require a huge amount of computational power. And we are confident that our next supercomputer, Setonics, will be a game changer in this respect. First of all, in contrary to Magnus, Setonics will have lots of GPUs, more than 750 AMD GPUs of the next generation. The machine learning workloads require modern accelerators to be effective and to be run in a reasonable time. This is because their high demand of computational power. A single modern GPU encapsulates the same computational power of around 33 Magnus nodes. And a single device, and it's encapsulated on a single device. And a single device is easier to program. Algorithms are easier to implement, and they are much more efficient. But still, even considering that, machine learning workloads today require more than one GPU to run to completion in a reasonable time. Other key factors that are important to consider are the number of CPU cores and the memory available on Setonics. In particular, we will have 128 CPU cores on each node, and the GPU nodes will have 512 gigabytes of RAM, which is a huge increase with respect to Magnus. We have around 5 times the number of cores, and then around 10 times the amount of memory available. So it's a huge improvement, and frameworks like TensorFlow can also carry on hybrid computations that is taking advantage of the number of the CPU cores available on the system, and also as well the CPU RAM. Another key factor is the interconnect. Interconnect, that is the network connecting the compute nodes. There will be an increase in performance also there. Currently, Magnus supports around 70 gigabytes per second of bandwidth, and Setonics will support at least 200 gigabytes per second of bandwidth. And in particular, the GPU nodes, the GPU partition will have up to 800 gigabytes per second. So this will enable distributed computing, in particular distributed training of machine learning models, feasible. So large-scale distributed training for deep learning network, deep neural network. Finally, we have a new file system, a new lastre file system, which is based on an hybrid technology, which mixes the fast SSD partition and a very large in size partition of supported by also very fast hard drives. So there will be a lot of space to store and process data sets. Thank you.
Thanks, Christian. I think there's a lot of exciting things coming up there. I'm sure all the users are excited to have their hands on it. So moving forward, Matthew, can you please talk us through how the future of renewable energies can be unlocked by AI and machine learning?
Sure, that's quite a blue sky question. I like it. I think the design and operation of one renewable energy converter is a complex problem, but things become a whole lot more complicated as soon as you start looking at arrays of renewable energy converters, or even microgrids, which are a combination of several sources of renewable energy. For example, one question that a grid operator has to answer constantly is that of load balancing, where you're trying to match the power demand with the power that is being produced. That is a soluble problem when you're dealing with on-demand sources of energy, which are coming from fossil resources. When you're dealing with renewable energies, it becomes a lot more complex. Not only do you have to predict what the demand is going to be, but you have to be able to predict what the weather is going to be with high accuracy in order to predict what your production is going to be and what farms to bring online, what farms to bring offline in real time. And I think machine learning here has a key role to play to allow us to integrate sources of renewable energy in our energy mix, either by helping us analyze the immense amount of data that we're gathering every second using unsupervised learning methods, for example, and helping us make decisions, operational decisions, or simply by running prediction models or even making operational decisions in our place using reinforcement learning. Another example of where machine learning could play a key role in the future of renewable energy is, for example, if you look at an array of wave energy converters, we have this thing called the Q factor, which is essentially the ratio between the production of the array as a whole and the sum of the production of each member of the array if they were operating on their own. That Q factor, if you operate the array in an optimal way, can be greater than 1, and the array can benefit from the interactions between the members of the array. Now, I can't start to begin to imagine how complex it would be to write control laws that would aim to maximize the Q factor, because not only you would have to model each of the wave energy converters in the array, but also the interaction between each energy converter and all the other members of the array. Whereas reinforcement learning, a controller would be able to observe, learn, and optimize the operation of such an array without us having to explicitly write the control laws to do so, which would be great. So if I summarize all of that, I think machine learning and artificial intelligence shows great advantages where we're trying to solve problems where even writing the equations you're trying to solve in the first place is a complex task.
Thank you. Thanks, Matthew. And if I put that question, put a similar question to you, Ivy, you've spoken about all that huge amount of data that's becoming now available, and Christian gave an update on what's proving in the technology, what advancements are coming there. So with now that being available or going to be available soon, how do you think this will change the way of our understanding of the universe?
Excellent question. So definitely that the new instruments are opening up brand new parameter space for us to explore the universe, and machine learning and AI basically enables us to systematically advance our understanding in a much more automated manner than ever before. And not only that, we will ensure that we're maximizing the science returns to each of the research teams from the investment that we've made into these future facilities, because these future facilities really take us to that next step, and it's not for free in terms of, not just monetary or people resources, but there's been a lot of effort to ensure that, yes, not only will we get this data, we would get good science out of the data. And machine learning is crucial to that. So there's that. that shift has happened, by the way. It's not just happening now, it's happened in the last 5 years. People are starting to realize that, yes, we do have to turn to newer methods.
Absolutely. Thank you, Ivy. So, Alessandro, what do you see as the future of AI and ML?
Yeah, thank you, Kamati. That's a good question. Well, from my perspective, I see AI and ML in the future to be more and more connected to other scientific domains. As Ivy has said, and also Mathieu has pointed out, actually we need machine learning and AI methods in simulations, in current simulation code, because the two worlds now can finally be merged. And I think we will finally start seeing machine learning and AI methods just as methods for getting solutions, getting information from your data, and not just like something a bit like a magic or black box which you use in some cases with static data, and then you see the results and try to understand it. I think we will trust it even more, like this approach will be trusted even more by scientists in the future, and we will benefit in terms of time to solution, in terms of new insights in the data, in science, and in control, for example, as Mathieu said. And all of this is in the future of AI is really now closer than ever. And I'm super confident that this will be the future of science, not only the future of AI and ML.
Sounds good. And what would be your advice to the new generation of researchers?
Yeah, well, take an AI and ML course as soon as you can, right? And for sure, explore the new opportunities. Don't just stick with what's there now. Everything can be reinvented. Everything can be updated to the current state of the art. And the current state of the art is AI. And we will have to teach people to just use AI as much as they can whenever it fits, because it is now something that on systems like Cetonix will be so easy to do that it would be a waste not to do it, right? You will have the computational power, you will have everything at your hands, you will have the libraries, have everything. So why not using AI and ML?
Thanks, Alessandro. I think there's a lot of questions and comments going on in the chat. What we would do, I mean, first of all, thanks to all the panelists for providing all those wonderful insights, and also to Mathieu and Christine to give some insights to what's happening in Cetonix. So we will quickly run. So I'll probably give an update about the machine learning community of practice, the national machine learning community of practice that I spoke about in the initial introduction. So the National Machine Learning Community of Practice was launched late last year, what we call as ML for AU, which currently has 100+ members, and it's been growing since then. So it's an initiative of the Australian Research Data Commons platform project called as Machine Learning Environments at Scale, which speaks about most of the aspects that we spoke about in the discussion here today. So the community of practice was launched with an interest of bringing both the researchers, the users, as well as the support community who are providing AI, ML support to our researchers, and look at what are the challenges that each of these communities face, and how we can work collaboratively to solve these challenges, not at any particular institutional level, but at the national level. So that's the whole idea of the ML Corp. It has 4 sub-communities in it now. So there's a researcher sub-community who are the users who come and speak about their challenges. There's a set of community around training, which is more around what Alessandro spoke about, right? So what are the challenges if we have to train our researcher cohort, what's available, what's not available, and what we need to focus on, and how can we bring some of these trainings, which are going to be really useful for this community rather than what's available off the shelf in some of the more platforms. The practitioner communities who are hands-on machine learning specialists, what kind of challenges they face in supporting our researchers and how we can support them. And the last one, but not the least, is the HPC community as well, the users of HPC environments who come and speak about what challenges they face currently, or what would they like this HPC environments to address for them to accelerate their research by applying AI and machine learning. So that's the ML for AU about. So Pawsey and ML for AU will be working together to create a sub-community, what we call, probably what we would call as AI, ML in HPC environments sub-community, which is more to bring all this group come together, start discussing about what kind of challenges, what are the new opportunities, what we should focus on, and how, and also in a kind of a forum to share knowledge and provide peer-to-peer support. So with that, probably before we go on break, I think Karina is going to share a Menti question, which is more to understand what is all your expectations around what this AI/ML community for HPC should be. And so I think Karina, you posted the, yeah, so there it is. So there's already responses coming, so that's good to see. For those who have not done yet, there's the code on the top. So we'll leave this on. Maybe we'll take a 5-minute break before we come back and start looking at questions in the chat, and also open the questions to the participants here. And hope to see some bigger responses when we come back in 5 minutes.
Thanks, Kamathi.
Great.
So 5 minutes. So Karina, do we want to start or give some more time?
Yeah, I have stopped sharing the screen. Thank you.
I think we're good to go ahead. There's a lot of great questions.
Oh, there's a lot here.
Yeah, there's a lot.
Yeah.
And there is a question in there that is totally off around quantum. Yes, we do. Is quantum computer being explored? The quick answer is yes. And there are, I believe, some recordings out on the Pawsey website that you can go. We just did a Nvidia CU quantum session. There's sessions on Pawsey working with quantum brilliance. There's a few out there. So, and we did another, yeah, there's sessions out. So I will, while we're doing through questions, I'll pop that into the chat as well.
Thanks, Anne. I've got the list of questions here. We can go one by one, or and before we open up for questions, I mean discussions here. So the first one I've got here for the panelists: do you see the role of FPGAs in future HPC systems such as photonics for ML and other apps? So I'm going to look at Mathieu or Christine, if you want to.
I'm happy to answer that. Actually, I think this question is well aligned with a couple of others that were asked. So I'll try to answer 3 in a row. So the first one was around TPU. The second one on FPGA, and also the question about quantum computing. So yeah, as a national facility, we are working with so many scientific disciplines that it would be stupid, and we need to be open. We're stupid not to be open-minded. We need to be open-minded and look on all the available technologies, including various accelerators, GPUs, FPGAs, TPUs, and also edge computing devices. With regards to decisions related to the current infrastructure, so basically to photonics, timing, and schedule of availability of various supercomputing technologies, and is a very important part of any supercomputing procurement. And one might actually say that it's actually one of the key factors deciding on what technology is becoming available. The other thing is that we need to make sure that we are covering both AI, machine learning, scientific simulations, and mixture of both, as I mentioned before. We believe that the architectural decisions that we have made for Setonics was the best given timing and the support that we need to provide. However, in future, you might expect, and we are already doing that, we will be looking at all the other accelerator and new technologies that can provide acceleration to data processing or simulations. We are also very close, as Anne mentioned, to the installation of our first quantum device here at Pawsey. And actually, as part of the Quantum Pioneers program that we are running, we have an industry partner which is looking at designing quantum machine learning algorithms as well. So there is a direct connection to today's session as well. But technologies like FPGAs are also being used extensively in SKA precursor projects, so both MWA and ASCAP for processing data. The development is actually very very extensive in terms of the number of devices that are being used there in the desert to process amazing amounts of data.
Thanks, Mathieu. I think you've addressed a few questions there. So I'm just going to jump around the questions and I'll leave it to the participants to put their hands up and ask if probably I missed something there. There's a question to the panel around how large a data input volume do you need to use to train the wave prediction network?
Sure, that's one for me, I think. That's a good question. And it's a hard one to answer, definitely. But what I can say is that so far, based on the work we've done on synthetic data, using synthetic data and also physical data from a wave tank testing campaign, we've needed a few hours in each sea state. So what we call sea state is a combination of a given wave height and a given wave period, and that the sea state is constantly evolving in the ocean. We've needed about a few hours of every sea state, but it's hard to answer definitely the question for the final version of the wave predictor, which will be deployed in the ocean, just because of the vast variability of ocean conditions. So far, a few hours have been good to have acceptable accuracy on a range of sea state, but we probably didn't expose or couldn't expose the wave predictor to the same amount of variability that would have to be exposed to in the ocean.
Thanks, Mathieu. Mathieu, while I have you here, there's also another question for you. Is there any paper or resource on wave predictor using neural network, which can predict up to 30 seconds into the future?
We haven't published any papers yet. There is a page on our website about the wave predictor. And I've also given, I think it must have been a 40-minute webinar as part of a Blue Economy CRC event. I can look for the link to the recording of this webinar and post it on the chat soon.
Thanks, Mathieu. I think they also indicated that there's an interest in knowing more about the training data set. So I'll probably leave it with you to pass some information there.
Sure.
Thank you. So there's another question, which probably is for the whole panel. What does the panelists think are the biggest barriers to AI reaching its potential in their fields and other applications across the economy and society? Question from Andrew Newman.
So I guess this is directed towards researchers who have spoken here as a panelist, because he speaks about the impact of AI in their research.
Yeah. And I think we covered some of this question, right? So we did have Mathieu speak about what is the impact around this, and Ivy also touched a bit on that. Is there anything else that the panelists want to add? And or Andrew, if you had any specific questions, could you please? Yeah, Ivy, go for it. Thanks.
Sorry. So one of the things we battle with, at least for supervised machine learning, is what is the ground truth? Because if we're looking to explore something that's unknown or discover unknown unknowns, we have to actually train our algorithm to find these unknown unknowns. So what do we base it on? It's kind of philosophical. It's kind of annoying like that, but this is a real problem. So there you go.
Thanks, Ivy. Andrew, did you want to add anything there, or should we move on to the next question?
I'm happy to go on to the next question, Kathy. But Ivy, that's a very insightful answer in terms of the philosophical underpinnings of the whole problem.
Thanks, Andrew. So the next question we have, again, I might have missed some question, I'm not sure, but I'm just going by the order of what I've got here. So the question I have is, with IoT, GIS, etc., cities are becoming awash with data. Have there been any suggestions, example from ORIN, the National Urban Data Platform Network, for potential urban planning applications? Looking if there's anyone.
If there are audience members too who want to speak on this, that might be interesting.
Yeah, I also don't know who raised this question, so.
Sorry, it was, can you hear me?
Yep, Ms. Bob.
Can you hear me?
Yes, Bob, we can hear you.
Yeah, okay, sorry, Bob Webb here, yeah, from the ANU. Yeah, I suppose I raised it from, we've been doing work on urban planning and effectively moving towards what is called, in the academic area at least, the science of cities, of trying to actually think about how, from a more data point of view, with the increasing amount of data that's now available from all sorts of sources about cities, and understanding the complex interactions between urban subsystems, you know, how this data can lead to a better understanding of something that so far has been beyond the reach of normal urban planning research or indeed practice. And I know ORIN is that body, which is a nationally funded body through the federal government, has been thinking about you know, how AI and related things might actually be brought to bear on here. I was just wondering if anyone in the seminar knew of any expressed interest, on whether Pawsey itself had been contacted by ORIN, or whether in fact there were anyone else who was aware of that sort of application into a very complex systems-based urban context.
Yeah, that sounds very interesting for us. What I wanted to say is that I believe that 2 years ago, no, sorry, maybe this COVID thing, so probably 4 years ago, on one of the supercomputing conferences, actually the main one in US, one of the keynote talks was covering that exact topic. I might be able to look it up and send some more details on that if you would be interested. Yeah.
I'd be very interested indeed on that. I mean, it's something that we're intending to pursue further with ORIN anyway, and with we're working with a network of urban researchers around Australia. So indeed, that would be of interest. If you can find that, that'd be great.
Cool. Thank you.
Thanks,
And perhaps I could just ask, as somebody who's not familiar too much with Pawsey, if there was that sort of interest, how do you take the first, and Pawsey seemed like a potential vehicle for, depending on the nature of the issues and the data. How do you take the first step on that? to actually engage with the Pawsey infrastructure.
Yeah, so that's very tightly related to the allocation models we have, and with Setonics, in next couple of months, you will see announcements of an allocation model for Setonics, which will include a couple of new possibilities for engaging with strategic projects. A big part of the system will be still allocated through merit allocation calls that we are running, so NCMAS, Pawsey Partner, and others. But there will be other possibilities. So yeah, keep an eye on that, and there will be some more announcements coming.
Thanks for that. Thank you.
Thanks, Mathieu. So that's all the questions I have here. We can still open some questions. I think we've got some more time. So if there's any questions, I'm just going to open my screen. Please raise your hand as a reaction so we get to see. Or please feel to.
I think there was a very interesting question, which was already answered by Mathieu. I think it's worth to iterate over. So the transition from Nvidia to AMD. I think, as Mathieu said, it's a new technology, new hardware vendor, and there will be some changes. But AMD is providing very powerful and effective tools to make this transition easier and as automatic as possible. So we've tested it, we've played with it, and it works. And it's the effort in porting applications, it's much reduced. And the results, it's also worth noting that AMD is it's a newer player with respect to Nvidia, but is providing, is putting lots of effort, and we can see almost daily improvements on their frameworks, and they are very responsive on. We've provided feedback on features. We provided bug reports, and they were very responsive to that, and we could see over the year an improvement. Visible improvement over their technology. So we are very confident we can provide the same the same core services that are currently supported by the Nvidia platform. Of course, Nvidia is older, it's in the game for a longer time, but the core services, core features that Nvidia provides will be also provided by AMD.
Thank you. Thanks, Christian. And I think there's also some interesting comments going on there. Jess, you've got questions, so probably you can.
No, thanks. I think Mathieu answered it. I was querying about the volume of data that went into training the wave predictor, and he's indicated it was about 250 gigabytes. So I think that was the synthetic wave data that was used to train the network. Is that right, Mathieu?
That's correct. That's the amount of data we generated using Magnus.
Right. Okay. Thanks for that.
Okay. Yeah. Thank you.
And I think there has been a few questions about how to access Pawsey systems and how the service works. And if they're free, the services at Pawsey are free, will pay by all of us through our taxes. But we're going to have some training sessions and some information sessions when Setonics phase 1 arrived. So keep your eyes open, and if you want, you can register to Pawsey Friends through our website. It's a link at the top right corner that says Pawsey Friends. You can put your details there, and you will get newsletters and get all information about the training that we do.
Thanks, Karina. Any other questions from participants?
I think when I was going through the questions in the chat, I also noted that there was a question about the investment and how to ensure that the technology remains cutting edge, and which is actually a good question, and does so basically that it will not become obsolete in, say, 10 years time. What I wanted to say is that I think GPUs are not a new technology anymore. I guess Ugo would be able to provide more detailed comments because he is in the, let's say, GPU business for much longer time than I am and any other Pawsey member. But yeah, just as an example, Titan system, which was I think installed in Oak Ridge around 2012, has all of its nodes based on GPUs, and it was for scientific simulations. And that was a couple of years ago, and that system became the biggest supercomputer in the world. I think Ugo actually had some experience programming GPUs before things like CUDA became available through things like OpenGL, so languages that are available for graphics, but you can transition also your codes, scientific codes to that. I guess this is the time for now. For us, this is a time that we actually have decided that the maturity of all the tools and availability of all the tools, the time is now that we can finally build and support GPU technology for general science, but also for AI and machine learning through Setonics. And part of it is the experience that we've had that Christian already covered. But for making sure that you can deliver scientific discoveries on supercomputers, because I mean the supercomputing technology is exciting, but the discoveries are the most important. You must have tools, compilers, libraries, scientific ecosystems, profilers, debuggers available, and we are quite confident that Setonics will be providing all of that for you.
Mathieu, sorry, since you mentioned my name a few times, I was going to say this. So look, no, you're right. I mean, the first GPU I programmed with graphics APIs was 1994, the SGI reality engine, right? So that's it. So the problem, I don't think is technology. I think is getting scientists and engineers up to speed with the technology. Because if you look at the CUDA API, for example, past CUDA 5 or 6, there are not that many people who know how to use the API properly. Even the tensor cores that are available, for example, in the NCI system, right, on the Volta GPUs, are not that easy to program directly. So I think I understand that people are concerned about aging technology, but I don't think there are that many people who are able to exploit the power of the current technology, right? So that's where we have to work on pretty hardly, right, with education, training, and for knowledge sharing and these kind of things. Because these GPUs, if you have to program them directly, are hard. Intrinsics are supported, which not many people know about, and so I would say that the challenge is really to get the community up to speed with the technology more than being concerned about the new technology, right? That's my take on it. Yeah.
Thanks, Ugo. And thanks, Mathieu, for picking up. As I said, I probably might not have followed all the questions there. So if there's any other open question that I have not picked up, please feel free to raise it here. And okay, so I don't see anything new coming up. Ugo, I think on your point, right, specifically, I think that's also one of the purpose of the community of practice, right, to come together and start speaking about what technology is available. What do we have to create more knowledge and awareness among our users so that the technology is used efficiently. While we look at sustainability of the technology, we still need to use it to the extent what power and capacity the technology provides. And that comes more through trainings and giving hands-on session to our users and creating that more awareness, more documentation like Christian spoke about. I think that's all something which I invite all of you to come and participate and have those discussions in the community of practice. So Karina, I'm not sure if you or the Pawsey team, do you want to add anything more? Are we?
I think I need to thank you all for an incredible event. Unfortunately, as you probably heard, I just find out that we have we didn't cap the event, but we only allow 100 people to join today. So we were the 100 lucky ones, and there were people who couldn't join. They probably will need to enjoy the recorder instead, and hopefully join the community to have this discussion with all of you. I think the community of practice is a good opportunity to remain connected, to keep the microphones open, and for us to listen, how can we help our community better? So please join the community, participate, share what you publish, share what you are doing in ML and artificial intelligence. I have to say, I search, and it's not many researchers working with ML and artificial intelligence in Australia. So those one who are doing it need to share what they are doing and what they are publishing, and probably get the newbies in the room. I think we still have Nyaga and Nana around, excited and taking advantage of these opportunities. So thank you to Ivy, to Alessandro, to Matthew, to our MC who kindly joined today to keep the discussion going, and to our experts who are always finding a space to have these conversations with the community. And we're gonna send a survey to reinforce messages around the community of practice and to have more clarity of which topics you want us to bring up to that community, and to see how can we improve these events in the future. We're gonna keep running events. I think in the next 2 months we will have one for manufacturing, which will be our September theme, and I think November theme will be renewable. So we will have these discussions around those topics coming soon. And I think that's all for today. So thank you very much.
Thank you. Thanks
Thank you,
to all the
Kamati.
panelists. Thank you.
Thank you.
It's
Thank
very
you.
interesting.
Okay. See you all.
Thank you. Bye.
Thank you.
Bye.